5. Rational functions. These are the most complex functions that we've looked at so far. So there are 3 different types that we can look at. Type 1, type 2, and type 3. No one calls them that way. So the book doesn't say that. I split them into 3 categories so I can summarize for my students what we're looking at here. Okay, so I'm going to give examples of each, and then we're going to discuss the differences. So one example of type 1, so a rational function is a polynomial over a polynomial. So x minus 1 over x plus 3. A polynomial over another polynomial. The numerator doesn't have to contain x, but the denominator has to, at least the denominator. Here's another example. Let's say x squared minus 4 over x squared minus 9. These are 2 examples of type 1. Type 2, f of x, 1 over x plus 4. Another example, f of x is x minus 1 over x squared minus 1. These are 2 examples of type 2, and here's type 3, f of x equals x squared plus 2x plus 1 over x minus 1, and f of x equals x squared minus 4 over x minus 3. Okay. Are there other types of rational functions more than type 1, 2, and 3? Yes. But they're way above our heads in this class. We're not going to look at more than these 3 types. And if you take calculus after this, like Math 230, you're going to see more details and a slightly different approach. Okay. So let's look at type 1. What do you notice? Forget about the other 2. What do you notice in type 1? Is there anything that says, oh, I think I know what's the deal with type 1?
The x on the top and the x on the bottom are the same.
You mean the type 1 has degree n over degree n. Same degree. Top and bottom, same degree. Type 2. Type 2 cannot have same degree. We're done. Same degree is just type 1. What can we say about type 2?
They're missing a degree.
Say that again?
Like the top part is missing a degree compared to the denominator.
No, it's still about the degree. That's the only difference between these 3.
The degree in the denominator
is higher, exactly. So degree n, and here degree greater than n, not equal. So higher degree in the denominator. Whatever, but higher degree. Not the same. Perfect. And now type 3. What would you say about type 3?
The degree is lower.
The degree is higher in the numerator by exactly, let me change this. I can give another example. So degree higher in the numerator by exactly by 1 unit. So if the denominator has degree n, the numerator has degree n plus 1. Degree 4, degree 5. Degree 3, degree 4. Degree 1, degree 2. Degree 2, degree 3. So higher degree in the numerator, but exactly by 1 unit. Exactly by 1 unit. If it's more, we cannot address it this class. So same degree over same degree, higher degree in the denominator, and this one has a higher degree in the numerator, but by exactly 1 unit. Degree 3, degree 4. Okay, let's start with the first one. Of course, we have a long list of stuff to show here, like we had with polynomials. Some transfer. Number one has to be the domain. This must be first dealt with. This is a must. In the past, I said domain is among the top, but not, I never really said it must be the first one. I don't really like how this camera sits here. Okay. Number two. Based on the domain, this must be the second item. Vertical asymptotes. We don't know what this is. I'll explain. So this is the first one. I'm going to box it in because it's new. And I will continue. And the function behavior. Left and right. Of the VAs. I'm going to abbreviate vertical asymptotes by VA, or vertical asymptote. Three. And behavior, which we know. And something we don't know. Horizontal asymptote. I'm going to circle this one because it's new. The end behavior is not new. We looked at polynomials with end behavior. 4. Of course, x-intercepts. 5. Y-intercept. 6. Max-min. Yes, with TI-84 or 83 or 81, whatever you have. 7. Range. The x-intercepts, of course, I should always remember that for moving forward, and multiplicities. Multiplicities. Y-intercept, max-min if they exist, and the range. Okay. So we have time to, I think, hopefully finish one problem. So I'm going to look at, maybe I should also mention here, potential, yes, I would like to write that 8, potential holes in the graph. And we'll talk about that. Okay, so let's look at f of x. First one, x minus 1 over x plus 3. Now, before I explain or we go through those steps, let's first identify or talk about what a vertical asymptote is and what a horizontal asymptote is. If a function is not defined at, let's say, x equals -2, the function cannot cross this line if it's undefined. So if the function does this, getting closer to that line, to x equals -2, from the left, let's say to infinity, and let's say from the right, it's going to -infinity as an example. Then x equals -2 is a VA. The function doesn't exist here, it cannot cross it, and the behavior of the function is -infinity on this side and +infinity on that side. That's what a vertical asymptote and the function behavior left and right of the VA represent. The vertical asymptote, the function is undefined at -2, and the behavior of the function could be one of the four situations. Both positive, both negative, one positive, one negative, or the other way. These are all four possibilities. That's what a vertical asymptote is. What is a horizontal asymptote? This is a horizontal asymptote. Because the function, as x increases to +infinity, the function values get closer to 0. As x goes to -infinity, the function values get closer and closer to 0. So y equals 0 is a horizontal asymptote. And how we determine them, you'll see in a moment. This is very simple, and I'll explain how we determine that in a minute. Okay, so coming back to our example, we will get our table going like we did before. And I'm going to check off the list all these items that we go through. So the first one is domain. Can anyone give us the, let me copy it here. F of x equals x minus 1 over x plus 3. Can anyone give us the domain of this function? Or at least tell us what x cannot be for sure. What x cannot be in this function?
-3.
Thank you, I was just sipping home. Very good. So at -3, remember 0 has to be in the table at all times. But because at -3 the function is undefined, this is how I signify undefined. No number, I cannot put anything underneath. You can write, if some of my students invented this. And they write undefined. It's fine too, whatever. Instead of those bars or nothing. That's fine. Because I see that x is undefined at the function is undefined at -3, right underneath this, I will write x equals -3 is a VA. So I have the domain already done. I identified the vertical asymptote done, but I did not identify the function behavior left and right. I know that this function is undefined at -3. And I know that left and right, it has to have infinities. What I don't know the sign of the infinity. Not a problem. Imagine, I'm not going to put these numbers in the table because I'm not going to use them again. A number to the left-hand side of -3 will be like -3.1. Very close as I can. On the other side will be -2.9. So here's how I determine the sign of these infinities. -3.1 minus 1 is negative. -3.1 plus 3 is negative. When I divide the negative by negative, it has to be positive.
If the graph is undefined at -3, then why is the vertical asymptote -2?
Oh, this was my example. This is not the graph of this function. Sorry, my apologies. It has nothing to do with this function. I was just here explaining what the vertical asymptote represents and how we get it, and what a horizontal asymptote is. But this is just a side explanation. Let me put it in so it's not confusing. Side example. Thank you. To determine the sign on the other side, -2.9 minus 1 is still negative, but this time -2.9 plus 3 becomes positive, and when I divide a negative by a positive, the sign is negative. So what have I accomplished so far? End behavior. And this is the law or the rule for type 1 horizontal asymptote is y equals leading coefficient of the top over the leading coefficient for the denominator. Can anyone tell us what is the leading coefficient of the top? Make sure that they are in descending order. The leading coefficient of the top is? Anyone?
1.
And the leading coefficient of the bottom is?
1.
So 1 over 1 is 1. And that is also the end behavior. Y equals 1, horizontal asymptote. So this is done. X-intercept. So when y is 0, remember a fraction is 0 only when the top is 0. So at x equals 1, the function is 0. Done. Y-intercept, I have to plug in 0. F of 0, 0 minus 1, negative 1 at the top, 0 plus 3, 3, negative 1 over 3. And I put it in the correct max-min, the calculator range with the calculator, there are no potential holes. Good. Let's graph. I don't care about any other information than my table. That's it. When we graph functions with asymptotes, we have to graph the asymptotes first. So I'm going to graph the asymptotes. They are not part of the graph. There is a vertical asymptote at negative 3. There is a horizontal asymptote at 1. And now I'm going to graph the function. I have to plot 0 for x, negative 3 for y, negative 1/3 for y, and 1 for x, 0 for y. Okay. The function is coming from 1, from approaching 1, going to positive infinity. From approaching 1, going to positive infinity. That's what this says. This piece is done. On the other side of the vertical asymptote, it's coming from negative infinity. It's crossing at 0, negative 1/3. It's crossing at 1, 0, and approaching 1. Do not touch the asymptotes, please. So this is f of x equals x minus 1 over x plus 3. Very simple. The range now, I see it. Yes, 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 yes. No. Yes, 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 yes. So it's negative infinity to 1, union 1 to infinity.